We'll do the slope stability dynamic condition for the dam.
We either do that, or I was thinking the effects of seepage and stuff like that.
With the dynamic condition, right?
Right, yeah.
Okay. Since you gave me the this one for the slope stability, I will assume you will do the analysis, dynamic analysis for the slope stability problems. For that homework, did you change the order of the pages or whatever? I really could not follow your solution.
Oh, I may have. It may have gotten mixed up. It may have. It was a bunch of pages.
Okay, let me read the Corey's proposal.
It doesn't really make a lot of sense.
Study of earthen dams and the implementation of monitoring system. I guess this one is actually your master's research, right?
Right. But I haven't done anything on it yet, so it'll help me down the road.
My recommendation is do something that is not your research topic. If you do it for your research topic, it may not be fair to your friend. Do you buy the idea?
Well, I was just saying, because I hadn't done anything with it yet.
But you will do the,
But I'll do it later down the road.
okay, let's, to be fair,
Okay.
okay? So this one is rejected.
Okay.
Okay, something that is not related to your research area. Jimmy Jackson, soil and rock dynamics. So Jimmy does not have anything to do with the dynamics for his research. So this one should be fine.
Well, actually, that's just this class title, Soil and Rock Dynamics, but
Survey proposal of site in which needs your physical investigation to determine.
pretty much using the,
So you will talk about what kinds of techniques may be better for such and such a site?
yes, well, we used, it's a project we did for geophysics in Francis. But using like MSAW, ERT, and just to show where the seepage paths are and stuff like that. So it'd be using, that'd be correlating it to the chapters that we studied, the wave propagation, I guess, or recording.
Is this something that you already did for the didactics class?
Yes, sir. I mean, it's
Repeating it?
I mean, it's repeated. It is repeating it, but it's
It is
they
repeated,
don't-
but it's not
It
repeated.
was repeated for me, but y'all have never seen it. It's something that would expand y'all's knowledge.
See, this will expand everybody else's knowledge too.
Is there anything new that you added in addition to the previous one?
To his added to his class.
Yeah.
I mean,
For this term paper proposal, did you add anything new to the to your
I mean,
previous one?
I haven't yet. I will be relating it to the class. But
Okay.
that's,
Then that should be fine.
I haven't got that deep into it yet.
If you have some case study already, then if you add some additional dynamics component in there, then that is fine. Alex was proposing attenuation of waves through a given material a little more in depth, much more in depth.
Much more.
Geometrical attenuation and material attenuation, and explore the differences and similarities between the two. Okay, fine.
Oh, mine's horrible. Half the class we've covered, more than half the class we've covered everything my research is on.
Wait a minute, different method of underground cavern detection.
I was gonna go through the different methods we've gone over and go more in depth for when they're good and when they're not good. Because on certain sites, they would find the underground tunnel or cavern, on others wouldn't be possible. I really don't like that topic, but I haven't thought of anything else yet. Half the class we've covered
This
my
one-
research,
This one is the kind of commitment.
I guess. That's why I don't like it.
The topic itself is okay,
Yeah.
but you said you don't like it, right?
Well, I mean, I'd rather do something else, but I can't think of anything else as of this
Okay,
day.
then you got to stick to this one.
Okay.
Now, is this a paper or a
Project.
presentation?
It's a presentation on PowerPoints.
You don't have to prepare the written paper as far as your PowerPoint presentation materials has enough details, then that should be okay.
Okay.
Good deal. How,
That's
how
where I
long
was
of a
confused.
presentation?
We have, we got to include Gareth.
Yep.
He may,
He'll show up. I feel it.
yeah, we can get him here using the, what is that, Skype?
Okay.
We can get Sudi to come and present too. That'll cut into everybody else's presentation time.
If you want to present, that's fine too.
Yeah, you can present too.
So we have 5 of you, so let's say
Or 6 or
10
7.
minutes.
Oh,
Okay,
does that include questions?
includes catch questions. So let's say 8-minute presentation, 2 minutes questions and answers. Whoever exceed 10 minutes, the penalty is 1 minute, $5.
Man, I'm going to bring the bank then.
So we got to prepare for the next semester. Whoa, who is this? Corey? Oh, you could download the slope/w?
I couldn't get the dynamic to work with
It was a
that
weird program to use.
because it was only like a student-free version, so it wouldn't do dynamic, but it did static.
You did a static analysis?
Uh-huh. Well, I did the analysis without the earthquake, the KH value, so I just assumed that was the static.
Okay, I will give you the extra 1 day just for you because you did it, but you did the wrong way.
Okay.
Okay, it does not have to be slope/w, but it should have the dynamic component.
Yeah, I just couldn't put in that factor because it wouldn't give me that option.
Then you got the wrong software.
Well, I got another one on there on the backside.
Does it?
I
Did
got
it include the dynamic condition?
Yeah, that one did.
It says static loading.
Yeah.
Bentley GINT
It
software.
Well,
doesn't
I got
have that one doesn't have it on there. The next one.
The next one does. The next one has the dynamic.
Because you can turn it off or on, so you can get the static. and the
Okay, so
dynamic.
what acceleration did you use?
0.2.
Point
what you
two.
said.
0.2. So it looks like you guys use the same software. Huh?
That's probably a little bit different.
I used 2 different ones. That one and another one.
that one.
So those two gave you the very different numbers? Should
No.
not be very different.
Mine was really close.
Yeah, software itself really should not make too much difference. But when you turn on the dynamic component, then probably the
Easier for
factor
me
of
to
safety
find it
could
for
be
you.
very different.
Yeah, it was. We got a lot lower.
It ended up being 0.71 to 0.74 was the comparison. They both failed, but
On the analysis options, there was the classical way, and then there was something I can't remember. 1997.
that's just a note. That's my notes, just for later. I'll do it.
What did you say?
There was something on the analysis, like choosing the analysis method. Not the method, but what was it? It was either the classical way or then there was something 1997 somebody. Is that, what's the 1997? You don't probably know unless I tell you.
I know what you are talking about.
Because those are the only
Yanbu?
two
Yes,
options.
it's the method that they.
Yeah, it was
The name was Yanbu.
No, that was different because there was Bishop and then that one and a bunch of others.
Slope stability is the, one of the major problems in geotechnical engineering. There may be, let's say, minimum 10 different techniques to analyze their slope stability. If I exaggerate, maybe there are more than 3 different approaches. But there are some famous techniques like the Bishop's technique, Yanbu's techniques, Skempton's technique. Corps of Engineers always talking about, I forgot the name. But it really does not matter which technique you use. Actually, the techniques that Corps of Engineers always try to advertise, okay, I'm not a big fan of that technique. I'm not a big opponent of that technique because I don't like the Corps of Engineers philosophy on that technique, because those techniques, again, themselves do not make too much differences. It depends on how you use the technique properly. Okay. So they should not just say, okay, we will use this technique. That indirectly indicate that they do not really understand the basics of slope stability. Don't tell it to the Corps of Engineers guys. Okay. I mean, it's something like this one. Okay. Slope stability technique or softwares are something that you can see here. Okay. And when you, okay, input parameters. On those input parameters, it has the sections, boundary, W in crack, T cracks, whatever. Okay. What you can do is you can input whatever numbers in this table. If you have any special condition, you cannot incorporate it in here. But time to time, you will have some situation that, okay, that you need to incorporate some other information in your slope stability analysis. But this one just cannot do that. And Corps of Engineers, what they did is, okay, they figured out, I'm still thinking about the name of the technique they are trying to use. Not EM.
I can pull it up on my laptop.
You left them in a shoulder.
You take a trip down there and ask.
Huh?
Take a trip down there and ask them.
But anyway, what they are doing is they have some special situation in the layering system. So they are trying to see the failure line. Okay, usually we assume the failure line is the circular line. They are trying to see what may happen if the failure line is going through.
Multiple layers.
Huh?
Multiple layers.
Yeah, there are some multiple layers. If this one, let's say, like this one, if you assume, let's say, circular line, it may go this way. They really doubted the role of this one because this one was marsh layer, so-called marsh layer, has very low strength. So they are trying to extend the failure line to this one. Something like this kind of failure line. And traditional software just could not do that. So they, I really wish I can recall their name. Let's say that is the Nathan's technique.
I'm gonna pull that.
Nathan's technique really cannot do this one. They are advertising that, okay, we are using Nathan's technique now, we can see what may happen if the failure line goes this way. But actually what they achieved is they worked with the U of Texas. There's a guy named Steve G. Wright. He is the slope stability guy. Actually, he tweaked his software a little bit, not the fundamental slope stability theory. Okay. He tweaked his software so that it can search the failure line this way and that way. It's just numerically he took the software so that he can search the failure line this way and this way, so that he can find out a kind of this kind of failure line that may have minimum factor of safety. Okay. Then, okay, I actually did not criticize Corps of Engineers because they are just too big organization for me to criticize. This technique is something like this one. Let's say you have the sibling, right? Okay. And you figured out you got to carry substantial amount of cargo. Okay. So you are trying to modify your sibling. You will just take out the back seat, and you will open the back space. And then what you should do is you got to stiffen the shocks. So you just replace all those shocks so that it has stiffer riding. And you may need to do something else to carry the substantial amount of cargo, right? Then you found out that you spent $50,000 to modify your sibling so that it may be, let's say, not completely equivalent to the Ford F-150. Okay. We know that even though you spend $50,000 and modify your sibling so that it can carry a lot of cargo, it will never even near to the F-150. If you have this kind of problems, okay, don't try to use this kind of software. Just go to the numerical software like the we have Abacus. You guys already use the SAP. Even SAP can do the slope stability analysis if you use it properly. Yeah. So what Corps of Engineers did was something like modify the sibling so that it can carry some cargo. Then my point is, why not just buy the F-150? But anyway, that is my philosophy. And so far, nobody really claimed Corps of Engineers for doing it this way. Sometime in the future, I think they will be really criticized.
The 6 methods they had for analysis were Bishop,
Uh-huh.
Thelenius, and Peterson, Spencer.
Spencer is the one that they are advocating.
This was the
Huh? Until
1045.
10:45.
What I was wondering about in the analysis methods, the verification methodology, they had the classical way,
Mhm.
and then according to EN 1997. What is EN 1997?
I guess that is Engineering News. Old name is Engineering News and Record. It's not a guy's name. That is it's something like the ASC. But again, those techniques will give us about the same numbers. Okay. Then let's talk about today's material. What's the lesson number?
23.
Dynamic bearing capacity.
There we go. Aw. I had your number today. I was gonna wait.
Dynamic bearing capacity. Objectives. Bearing capacity of soils will be different. When subjected to, or when subjected to dynamic load. And we need to know how to evaluate Q sub U, bearing capacity of the soil for dynamic load. Before I talk about some equations, we need to understand that there are many different approaches in geotechnical area. I mean, you may find out much more different techniques in the in geotechnical practicing area. Maybe it's better to say practicing area. Right. And for this one, okay, we really need to consider dynamic response of foundation itself. Foundation itself, I mean, foundation itself has the typically reinforced concrete, right? Reinforced concrete. And soils. Okay, because when soil is subjected to dynamic condition, its strengths can be different. Okay. So really, when we really want to consider the dynamic behavior of our foundation, we got to consider this one and this one at the same time. But it's usually very difficult. Okay. It's difficult, but it's not impossible, because can you guess why we can consider behavior of the foundation and soils under dynamic loading simultaneously? Your set can do those things. Okay. Usually the reason why that is so difficult is, let's say you have your foundation, this is your soil. When there is a vibration, okay, when there is a vibration, then it will cause some trouble on this, let's say, foundation block. Let's say, then the modulus of this foundation block was degraded. Then stress acting on the soil will be different. When the stress on the soil is different, then it will respond back to this foundation. So it's something like going back and forth. So the actual calculation should be, you got to compute the soil behavior. Then based on that soil behavior, you got to compute the foundation behavior. And based on the foundation behavior, soil behavior will be different. Then you got to compute back the foundation behavior. So it's going back and forth. That is so-called soil structure interaction. So that kind of repeated calculation is usually almost impossible for hand calculation or just using the calculator, but that can be done using proper computer softwares. Okay? So I would say this one is really SSN, so SSI, not SSN. SSN is Social Security number, right? SSI
For now.
from and usually solved by proper software. Okay. If I just say you got to have the proper software, then you can solve it, and probably I can stop the class at this moment and just assign the homework. But at least we need to check the dynamic bearing capacity of our soils using some simplified technique. Many simple projects, this simplified technique will work. If you are designing, let's say, the foundations for the launch pad of space shuttle, simple calculation may not be the good technique. Bearing capacity equation. This is the equation that we used in foundation engineering class. Correction factors plus Q prime n sub Q, correction factors plus 1/2 gamma prime B and gamma correction factors. Okay. In this correction factor, we know that we have shape factor for C term, depth factor for C term, inclination factor for C term, and similar terms are there. Okay. So we will intentionally stick to the same equation because we already have quite good knowledge of this equation. And if we can find n sub c, n sub q, n sub gamma for dynamic condition, it will be good, right? It will be good. But in real life, we don't have complete set of n sub c, n sub q, n sub gamma for dynamic loading. The reason is we don't have n sub c dynamic, n sub q dynamic, we don't have a complete set of because typically what may happen is, so this one is n sub gamma, this one is loading velocity, inch per second. Dry sand, submerged sand, search is for basic FL, okay? When you plot this figure, you don't have to plot it very accurately. I intentionally just remove the numbers on this side. Okay, then let's look at this figure. N sub gamma is one of the bearing capacity factor. This loading velocity is actual particle velocity, again, particle velocity, okay? That can be interpreted as loading rate. How fast? How fast loading is applied. Again, there is some. Wait. Let's say this one is your foundation soil. Foundation is there. Okay. Static foundation loading is stay there. In terms of loading velocity, this loading velocity is almost 0 inches per second. But when we have vibration, it will vibrate this way. So it has certain loading velocity, right? Okay. Usually, when you have fast loading, response of soil is higher. Reaction from the soil is higher. Can you imagine that? When you hit the water with real slow speed, water will not resist. When you hit the water with real high speed, something like when you jump into the pool and when you hit the water with your belly, you will feel big resistance, right? So in here you can see that when loading velocity is getting higher, somewhere here N sub gamma is getting higher. Somewhere here N sub gamma is lower. Okay. This behavior now it can be explained, but up to let's say 2000, early 2005, people could not explain this kind of behavior. Usually I teach why we have this kind of behavior in spring semester in the advanced soil mechanics, but you guys will miss it. Did you guys take the advanced soil mechanics? Some. Or You learned about the rate dependency?
We took advantage, what we take advantage? In foundation, yeah.
Did I talk about the two different rate dependency?
I don't think so.
Okay, anyway, okay, this one is the experimental result by Basic 1965. At that time, not only Basic, people just could not figure out why we have lower resistance in there. But again, now we understand it, and this behavior is completely correct. Anyway, anyhow, it's not really easy to make some formulation how we can reflect this loading rate to the bearing capacity calculation of the foundation. It's not easy. Okay? So I would say not easy to implement. So what we do is, okay, let's make everything simple and conservative.
So what if you had a clay dough instead of cement? Is that one the problem?
What if we have clay soils? I will talk about that maybe 10 minutes later. Okay, good question. Some additional findings from Basic is, Basic 1973, okay, found that internal friction angle for dynamic condition for sandy soils is about phi prime static minus 2 degrees. Roughly, okay, not exactly. Then probably what we can do is what? We just take the phi dynamic to compute n sub c, n sub q, n sub gamma. Phi dynamic. I mean, we can use the same table as in table 3.3 in all time foundation textbook. Just use the phi that is phi from triaxial or whatever minus 2 degrees. It's easier, right? This approach will be easier and simple. Then some other findings is punching failure is a dominant failure mode. When maximum acceleration from whatever vibration is higher than 13 G. This is from Hilbert, 1964. So when you have very high acceleration, then you got to actually consider the punching failure, not the general failure. But when you look at this number, 13 G, is very high acceleration, right? But most times we are not going to have this condition. But just remember this one, when you have very high G, it will be the punching failure. That will be something like, if I push this one will be pushed back. It will push the back. If I hit this one with real high velocity, maybe I just punch it through this back, right? Just exactly same behavior. Then one is for sandy soil.
How come it decreases instead of increases?
Huh?
How come when your fee, how come it increases, decreases?
Decreases?
Because wouldn't that just make it better? Less likely to fail?
I did not read that basics paper directly, but this is my guess. That's really good question. Let's say static answer gamma is this for this dry sand, static gamma, N gamma. Okay. Most places, dynamic N gamma is actually higher. In some cases, dynamic N gamma is lower. As a designer, we got to be conservative, right? So that's the reason why I guess that to be conservative, we will just subtract 2 degrees. And for clayey soils, the story is different. For clayey soils, typically C, U, undrained shear strength dynamic condition was somewhere 1.5 times C sub U static condition. Clayey soils has typically C prime is, C is the phi prime is 0, right? It will give us N gamma is 0, and Q is usually 1, and N sub C is somewhere 5 to 7, depends on which table you use. This number 1.5 times is also very conservative number. Again, think about the resistance from water. For the slow loading, resistance is almost 0. For quick loading, resistance is very high. Think about the airplane crash into the water. At the moment that airplane hit the water, then it will just crash into pieces. And this number again should be the very conservative number. Then I guess using this information, we can compute dynamic bearing capacity of soils. Is that correct? Okay. Forget about that figure. I used that figure to give you some basic idea. But when actually we design our foundation for dynamic loading, these 3 ideas will solve the problem. We will decrease the phi, we will increase the C, and for the high acceleration, we will consider punching failure. Is that correct? It's not correct. Think about why it's not correct.
Wait, say that again?
Using those 3 concepts or ideas, we can design dynamic bearing capacity of our foundation, soils. That means we can just decrease the internal friction angle about 2 degrees. We will increase cohesion about 50 times. And for the real high acceleration, we will just consider punching shear. Is that what we are supposed to do?
No.
then how are we going to modify?
We need to have something in there that relates the dynamic motion to all that. Right now, it's just, you're saying for any dynamic motion, it's that. And that's not.
That will be considered by so-called soil and structure interaction. But if we just think about the bearing capacity of our soil by simplified technique, this one looks like conservative design. How about this one? If we use or if we increase our cohesion 50 times, we may end up with some big trouble. What is that big trouble?
You get a very high bearing capacity. wouldn't you?
As far as we have really, truly high bearing capacity, we should be fine. But I will guarantee you that if you design your foundation on clay soils with your 50% increased cohesion, you will have the failure. Why? Why?
Well, because wouldn't your bearing capacity be higher when you calculate it? That's what I was saying.
I mean, if the soil really provides us high bearing capacity, no problem.
Well, yeah, that's a good thing, but it's like a, I don't know how to,
This is Jared. You may feel like this is a vibration because your screen is vibrating. Now, what is the static? What is the condition? Static condition. So in real life, we have the combination of static loading and vibration loading, right? You design your foundation based on the dynamic loading, but let's say machine just stopped, earthquake stopped. Then there is a static condition, and cohesion will be lower, right? The condition can be something like this one. During the dynamic condition, your foundation should be okay. When vibration stops, then your foundation can fail. Does that make sense? So even though we know this condition for real design, use C sub U, what, static or dynamic? Static. I think Nathan does not buy this idea yet.
no, I did. I had it backwards in my mind.
Okay? Because this condition is the critical condition for clay soil. Therefore, when I write bearing capacity equation again, therefore, Q sub U dynamic should be based on C static times N sub C plus Q prime N sub Q plus 1/2 to find out those bearing capacity factors. It's better to use P dynamic. Of course, when you have the fat clay soils, phi is essentially 0, then you have only the two terms. Then you don't have to worry about the phi. If you have quite the clean sandy soils, you don't have to worry about C because it's essentially 0. Any questions? I guess the concept is simple. Idea of designing the dynamic bearing capacity was just a little bit confusing, but I guess now you guys understood it. This one is the handout.
Sorry, the earth, your legs are getting weak.
I will go the other side.
Here, it's gonna get motion sickness.
I will come back.
Oh, okay. Oh, what's up?
How easy it is to compute the dynamic bearing capacity using this concept. I will solve one example problem. 6.1 in the handout. It says 3 feet square foundation supported by dense sand. Dense sand means C is essentially 0. Okay? So we don't have to worry about whether C dynamic or C static. And angle of friction. Oh, okay. It says relative density. We don't need relative density. Unit weight is 120 pound per foot cube. Internal friction angle is 38 degrees. Set static. Depth of the foundation is 3 feet. And it asks compute Q sub ultimate dynamic. It's the vertical one. Should be very simple. We will use this equation, Mayhoff's equation. Q sub U is C and C 1/2 Q plus, for the Q term, there's no 1/2. Q and sub Q plus 1/2 gamma B and gamma and it said C is 0, so we will remove this term.
News for the day.
Shot of the Mississippi.
Alright. Then let's try to find out n sub Q and n sub gamma. Okay. Or phi equal what?
Be 40. I mean 36 for dynamic.
36? Okay. This pen is not good. Do we have the chart?
I thought about bringing a book today, but
Which,
That'd helpful.
what
Yeah.
chart?
Bearing capacity chart.
Ah, no.
Nope.
I don't have the book.
Okay.
We can just guess.
Get n sub Q and n sub gamma from table 3.3. Okay. And let's assume n sub q is 50, n sub gamma is 30. Then q sub u dynamic should be 0 plus q is
Gamma times D.
q is 120 times 3 times n sub q was 50 plus 1/2 times 120. B was width was 3 feet. E and gamma 30. Okay. Those correction factors, you can find out correction factors from the table 3.4 and 3.5. Then that should be it. Easy, huh? Okay. But don't forget the discussion that we have in here. Okay, this one is just the simplified procedure. For the, the simplified procedure will work for simple structures. But when you have really important foundations, it's better to use some software that can consider solid structure in action. With this handout, you may wonder why 2 pages. Problem 6
I
point.
think that last page didn't need to be on there. I don't know.
6.4 and 6.5 is your homework.
6.4 and 5.
Killing the small ones, killing me.
It's not going to take a long time. This time, it's not going to take a long time. Okay, I'm
Look at that.
Hmm?
Good talk. Good talk.
So, if it was a good talk, then probably we got to extend it a little bit. When you have a real good movie, you wish the movie was a little bit longer, right?
No.
Right?
No, not
No. You get to go home and wait till it comes out.
When you pick the movie from, let's say, Walmart, you are using that
Red
the
box.
machine,
Red box.
red box. Then how do you pick the movie? Let's say you are just trying to pick a movie to kill the time with your friend or with your family. Then what kind of movie are you gonna pick?
One that I want to watch.
Huh?
One that I want to watch.
Action packed
Yeah.
field that's short and sweet. You know,
Short and sweet.
yeah, short and sweet. A lot of action.
I have a lot of
Okay.
action.
Okay. You said short and sweet. Usually, what I saw from my sons is, let's say, they want to watch, let's say, 3 movies.
They're trying to put you to sleep.
3 movies look good, and then what they usually do is they check the playing time. Okay. 120 minutes, 140 minutes, then they pick the 140 minutes. But the class is different, right? Good class should be a little bit shorter, so I will just close my lecture at this moment.
Oh, look at you.
Next one may take a little bit longer than 75 minutes, so I will just, I saved 10 minutes from today's lecture.
That'll be good talk. Good talk.
Okay.
You want
When are
donuts?
we doing the presentations?
Actually, the
Week we come back, last class,
last class
before finals.
before the final, so there should be
It'll be the,
second class
Thursday.
after Thanksgiving.
yeah, it'll be Thursday. we
After
come back.
Thanksgiving? Okay.
After Thanksgiving. If you want to have a presentation before Thanksgiving, that's completely fine with me. Now you can just close it. It's not